Problem number 1. What is the sum of the 7 smallest distinct positive integer multiples of 9? Okay. Well, first thing we need to do is just figure out what this all means. Um, we've got a lot of adjectives here. We have 7, smallest, distinct, positive, integer. The noun is multiples. And then we have a preposition of 9. So multiples of 9. Okay, we know what multiples of 9 are, right? We know 63 is, whoops, didn't mean to do that. 63 is a multiple of 9, right? Or 27 is a multiple of 9. So we know what multiples of 9 are. Oh, we know what they mean when they say 7 and smallest. Distinct just means that we want different numbers. So we don't want to add a bunch of, we don't want to add 9 and 9 and 9 and get 7 nines, which are which are small, but they're not distinct. So we want them to be distinct. So we want them to be different. And then positive. We need to know what positive numbers are, and we need to know what integers are. So that's those are the key things, I think, are integers and positive. So let's take a look. What are integers? Integers are just the well, let me give you an example. Okay, so the numbers from minus infinity up to minus, say, 3, 2, 1, 0, 1, 2, 3, and so on. Whoops. All the way up to infinity. Okay? So what's special about these numbers? Well, integers don't have any fractional parts to them. Okay, so you see that like 1/2 is not an integer. 0.5. Pi is not an integer. That's 3.14159 and so on, going on forever. So all of these numbers have fractional parts. Okay, so 6.72. So it has this fractional part, 72/100ths is what that means. So these are not integers. Okay, so we're just looking at the numbers without any fractional parts. Okay, and integers include both positive and negative and 0. Okay, now if they had said natural numbers instead of integer, or if they had said counting numbers, or if they said whole numbers, that would be something different. So like natural numbers start with 1 and go on up. But whole numbers start at 0 and go on up. Okay? So it's good to know the definitions of those different sets of numbers. Because in this one, you're going to have the question, is 0 positive or not? Because if 0 is positive, then our first positive integer multiple is going to be 0, right? And then we would have 0, 9, 18, all the way up to 6 times 9, which would be 54. That's going to be a different sum than if our positive integers start with 1. Because then we'd have 1, 18, 27, all the way up to 63, which is 7 times 9. So we need to figure out, first of all, is 0 positive or not? And the answer is, I'm just going to tell you because it's just basically a definition. By definition, positive numbers are greater than 0. Okay? And negative numbers are less than 0. But 0 itself is not, it's not greater than 0, it's not less than 0. 0 is just equal to 0. So it's sort of in no man's land here. It's not positive, it's not negative. So when we add the smallest distinct positive integer multiples of 9, we would not include 0. Okay? So the set that we're dealing with is just 1, 2, 3 on up. Okay? So these are the positive integers. Okay? And positive integers are the same thing as the natural numbers. So we could also say Instead of positive integers, we could have said natural numbers. Or we could have said whole numbers. Okay, it's the same set. Okay. So, but if we had said non-negative numbers, then what would that be? Non-negative doesn't necessarily mean positive. It just means it's not negative. Okay. So we would eliminate. Oh, this should have been a negative here. We would eliminate all the negative numbers, and then what's left over would be the non-negative numbers. And in this case, non-negative numbers include 0. Okay? So watch carefully and think, read closely. Because sometimes, they might try to trip you up to make sure that you know what the different sets of numbers are and whether or not they include 0 or not. But in this case, we're dealing with positive integers, so that does not include 0. And so we're just looking at 1 times 9 and 2 times 9 and 3 times 9 and so on, all the way up to 7 times 9. Okay? So that gets you started. If you want to stop and work on it some more, you can. But I'm going to go ahead and give you the solution now. So we have a sum of numbers. These would essentially be 9, 18, 27. This is 63. There's a bunch of numbers here we left out. Now there's a number of different ways that we could do this. One way you might do it is you might notice that we have a common factor of 9 throughout this whole thing. So we have 1 times 9, 2 times 9, 3 times 9. So we can actually factor out a 9 by using the distributive property in reverse. And if you remember, the distributive property just says that C times A plus B is equal to CA plus CB. Okay? And so that's just saying we can distribute the C among the two terms in the parentheses. But it also works in reverse. If we have a common factor between the terms that are added together, we can actually factor them out and write it this way. So it works both ways. And it's good to remember that and be flexible with how you use the distributive property. Because what I can do is I can say that this thing here is equal to 9 times the quantity 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7. Okay? Since there's only 7, we can list them all out, and it's really not that much trouble. In fact, it's really not that much trouble to add these numbers, because I can take 13 plus 9 is 22, and then add 6 more, that's 28. And if I take 28 times 9, so 9 times 28, I will get 252. Okay, and that is the answer. Now, some of you may have watched my video on adding arithmetic series. Okay, and you'll notice that this is an arithmetic series because we've got 9 plus 18 plus 27 plus all the way up to 63. And if you look at the difference between consecutive integers, we've just got 9, right? We're just adding 9 each time. Okay? So if the difference between consecutive integers is a constant, then it's an arithmetic series, and we have a formula that we can use. And I'm not one to really advocate just memorizing formulas. I want you to understand where it came from, but you use it enough times and you're just going to remember it automatically. So if you remember the formula, it's the sum of this series is equal to the first number plus the last number times the number of numbers. Now we know there's 7, divided by 2. Okay? And that will also give you 252. Alright? And if you don't remember the formula, but you remember the trick, what we can do is we can write this as S, and then we can write S again, only backwards. 63 plus, let's see, that'd be 54 plus 45 plus all the way down to 9. Okay, so it's the same sum, it's just written in a different order. Okay, and if we add those up, you can see that this is 72, 72, 72, okay, and all the way to 72. Okay, so we'll end up with, this is supposed to be a plus, so we'll end up with this list of 72s that we're going to add up. Okay, and this, we've added 2 of these sums, so this is actually equal to 2s now. And this, so how many 72s are we adding up? It's going to be based on the number of numbers up here, which we know was 7. So it's going to be 7 times 72. And that's going to be twice the sum that we're looking for. So S is going to be equal to 7 times 72 all over 2, which is it's the same thing that we have here, right? It's the same thing, right? It's because 63 and 9 is 72 times 7 over 2, and that's how that's where this formula comes from, is by doing something like this. So again, we get 252, no matter how you do it, and that's a good thing, because if we get different answers, we made a mistake somewhere. In one of them, or maybe all of them, I don't know. But it's a good thing we can do it all these different ways and get the same answer. So there you go. Go on to the next problem.